Welcome to ERC Tipsnology. In this video, we will be doing the nodal analysis on series parallel resistors consisting of a voltage source and a current source using 5 resistors. So, let's start doing the nodal analysis and you will see how it is done. First, let's draw here a voltage source on the left side of the circuit. And let's draw another source in the form of a current source on the right side of the circuit. And then let's draw 3 resistors at the top of the circuit, and we will also put 2 more resistors in the middle part of the circuit. As shown here, I'm drawing the 3 resistors at the top of the circuit, and let's name it as R1, R2, R3, R4, and R5. Now I have labeled here VS and IS, and I'm now putting the names R1, R2, R3, R4, and R5 in our circuit. I am now writing 300 ohms, 400 ohms, 500 ohms, 200 ohms, and 300 ohms in our resistors respectively. And we have an IS of 100 milliamperes and a voltage source of 10 volts. So this is how our circuit is. The first thing to do in nodal analysis is to put here the VA and the VB as our name for the nodes. And at the bottom, let's put a ground, which will represent 0 volt. And then after that, let's make all of the lines or wires connected to the ground as 0 volt as a reference or common ground. Take note that the current here, IS, is 100 milliamperes, and let's start by drawing the current I1 away from VA or coming out of VA, and I2 as coming out of VA also, and I3 coming out from VA. This will be our assumption, so we may be wrong, but this is the easiest way to do nodal analysis. So in node VA, all the currents are coming out, so we can add them. I1 plus I2 plus I3 would be equal to 0. And by Ohm's law, we have I equals V over R for each of them. So we have V1 over R1 plus V2 over R2 plus V3 over R3 will be equal to 0. And we have to take the voltage V1 by following the current flow. So from node VA, we will follow it later. And let's draw here first the current coming from IS with a value of 100 milliamperes. Now let's start with V1. VA minus positive 10. Or VA minus 10 over the resistor, which is 300. In the case of V2, we can write VA minus 0 because the current I2 is coming out from VA, so it will be VA minus 0 over 400. So it's that easy. Plus the current I3 in Ohm's law would be VA minus VB. Alright, VA minus VB over 500 ohms. And there you go, we equate it to 0, and let's use our algebra knowledge. VA over 300 minus 10 over 300 plus VA over 400. And plus minus will be minus. So plus minus will become minus 0 over 400 plus VA over 500 plus and minus will become minus, so VB over 500. equals 0. And if you analyze the answer, we have here VA over 300. Let's make it 1 over 300 and factor out VA. We have another VA here. Factor out VA, it will be 1 over 400. And another VA over here, so plus 1 over 500. And let's factor out VA because they are common to them. And we also have minus VB. I'll draw a rectangle to easily see it. Minus 1 over 500 VB, and the constant of negative 10 over 300. Let's make it, let's cancel this 0 over 400, 0, and then the 10 over 300, when you move the negative 10 over 300 to the right side of the equation, the minus will become plus. Therefore, this will be equal to 10 over 300. This will now be easier for us, and let's use the calculator to compute for the fractional part of VA. 1 over 300 plus 1 over 400 plus 1 over 500. What will be our answer here? Let's see. That will be equal to 47 over 6,000 VA minus 1 over 500 VB equals 10 over 300. You may also write your answer not as a fraction but as a number of or decimal number of 7.8333 multiply, or let's make it 6 decimal places, 10 to the minus 3 VA minus, let's divide 1 over 500. What would that be? And we will have an answer of 2 times 10 to the minus 3 VB. And the 10 over 300 by using the calculator will become 0.033333. So there you go. We have our first equation by using the node VA. So we write it here. Let's write equation number 1 with respect to node VA. And so we will analyze another node, that would be the node VB. So in node VB, what will we get is, let's draw the current coming out from VB. Let's call this I3. And another current coming out from VB. Let's call it as I4. And another one coming out of VB. Let's call it as I5. Now, we will add the three currents by Kirchhoff's current law. I3 plus I4 plus I5 will be equal to 0. By Ohm's law, V over R, we will get V3 over R3 plus V4 over R4 plus V5 over R5 will be equal to 0. But by the way, we already know the I5, right? So we don't need to divide V5 over R5, but the opposite direction will be there. So the 100 milliamperes going to the left, and we assume it to the right, will become negative 100 milliamperes. But we have to express this as an ampere, so that would be minus 100 ampere, or to make it short, 0.1 ampere. That's our current source value, so no need to get the V5 over R5 because we already know I5. Now, what is V3 by Ohm's law or by KVL? That would be VB minus VA following the current direction, and that will be over 500 ohms, plus V4 will be VB minus 0. Just like what we did before, VB minus 0 over 200 ohms. And the last one, we will just copy our answer plus negative 1 or 0.1 ampere. Because we don't need to get the Ohm's law of this since we already know the current for IS. Now let's distribute this as VB over 500 minus VA over 500 plus VB over 200 minus, because this is plus and minus, that would be minus 0 over 200. and then we have plus and minus, so that would be, let's just cancel letter A, so plus minus 0.1. Now all the VB must be put together, and all the VA, and because we only have one VA, let's drop here minus 1 over 500 VA, plus let's add the fractional part of VB, 1 over 500 plus 1 over 200 multiply with VB, and there you go. And then the constant here 0, let's just cancel this, and the plus minus here would be minus 0.1 equals 0, because plus and minus will become minus, so 0. Minus 0.1 equals 0. And let's write it again, 1 over 500, negative 1 over 500, VA plus, let's use the calculator, 1 over 500, using the fractional function, plus 1 over 200 equals, we get the answer here of, let's write first the fractional part of 7 over 1000 VB, and the negative 0.1, we can move it to the right, it will become positive. So we will write here equals 0.1 only without minus. And then we can convert the answer into decimal number with maybe 6 decimal places or something. Minus 2 times 10 to the minus 3 volt VA plus 7 divided by 1000 will give us 7 times 10 to the minus 3 VB equals 0.1. This is just to show you the final answer for equation number 2, that is with respect to the node VB. So let's write over here equation 2 with respect to the node VB. Now that we got the two equation, we may write it again at the top part of the paper to make it easier for us to understand. Let's just use the fractional part because it's better for me to use it in the calculation. So let's write it here. The first equation, I'm writing it down, 47 over 5,000 over 6,000 VA minus 1 over 500 VB equals 10 over 300. And then the other one is negative 1 over 500 VA plus 7 over 1000 VB is equal to 0.1. Now, let's use a special function of the calculator to get the VA and the VB. This is the shortcut or the shortest way to get VA and VB. All you have to do is to press mode 5, and then press number 1 to get the X and Y variable and constant. So press 1, so mode 5, 1, and then enter the fractional part there, 47 divided by our answer there, which is 6,000, and then negative 1 divided by 500, and 10 divided by 300, and then press equal sign, and then enter the second equation value, negative 1 divided by 500 equals, and then 7 divided by 1000 equals, and the last one is 0.1 equals sign. That's it. You will get here the value of X, which represents VA. And now we got the VA as 520 over 61. That would be 8.52459 volts for our VA. We can copy here 2 more digits and round up 59 to 6 or 59 to 6. So we have 8.5246 volts for VA, and for VB, just press equal sign and SD and you will get the answer of 1020 over 61, which is 16.7213 volts. And there you go. We already got the VA value and the VB. So we now have the two node voltages using nodal analysis. And from there, let's go back to our equations where we say that the V1 is equal to VA minus 10, or we have to write all the values of V1, V2, V3, V4, and V5. So as you can see here, V1 equals VA minus 10. So we will subtract the value of VA that we got, which is 8.5246 minus 10, and we will get the value of V1. So let's use the calculator to subtract, but you need to put mode 1 again, mode 1 before you calculate. So I'm now subtracting VA minus 10, and I got my answer as negative 1.475 volts. And there you go, we have the V1. And from here, we can also calculate the other voltages. That includes V2. So let's see how much is V2. We say it's equal to VA minus 0 or equal to VA. Therefore, will be equal to 8.5246 volts. And we can get V3 as equal to VA minus VB. So if I subtract 8.5246 minus 16.7213, we will be getting the answer for V3, which is minus 8.1967 volts. And let's look at equation 2 for V4. We got V4 is V3 minus 0. So, or V4 equals VB minus 0. So we can just say V4 equals VB, which is 16.7213 volts. And finally, we have V5 is equal to I5 R5 by using Ohm's law. Since we already know the value of I5, so no need to do some subtraction or division, just multiply I5. But as you can see here, I5 is in the opposite direction of our actual source. So I'll be putting minus 0.1 amperes or multiplied with R5, which is equal to 300 ohms. And I'll be getting V5 as minus value because we used a to the right direction for I5, which is opposite the actual IS direction. Anyway, we got a value of minus 30 volts for our V5. And there you go, we have the voltages across each of the resistors in our circuit. And the last step, of course, is to get the currents in each branches. So we have I1 equals V1 over R1 by using Ohm's law, and we already know V1, it's minus 1.475 volts divided by 300 ohms, and we would be getting amperes as our answer because it's volt over ohm. The answer will be ampere. And let's see what we got here. We got minus 4.92 times 10 to the minus 3 ampere, or let's make this milliampere because times 10 to the minus 3 is milli. We got minus 4.92 milliamperes. And we will also calculate for I2 using Ohm's law, V2 over R2. Our V2 is 8.5246 volts divided by our R2, which is 400 ohms. So volt over ohm will be ampere, and we may convert the answer into milliampere by just moving the decimal point to the right 3 times. Let's see. We got the answer of 0.213.115 amperes. So let's move the decimal point to the right. We will get 21.3115 milliamperes for I2. And for I3, where will we put I3? Let's put it over here on the right side. But let me put a circle or Let's encircle the I2. Now for I3 by Ohm's law, V3 over R3. And V3 is equal to minus 8.1967 volts for V3. That will be over 500 ohms of R3. And let's use the calculator. Volt over ohm again will be amperes. And we can change it to milliamperes by simply moving the decimal point to the right 3 times. Just like here, we got 0.0163934. Let's move the point to the right 3 times. And we will be getting 16.3934 milliamperes. And there you go. We got the current flowing through R3, which is called I3. 2 more currents. Let's look for some space over here. Let's put I4 is equal to V4 over R4 by Ohm's law. So V4 is equal to 16.7213 volts divided by R4, which is 200 ohms. And let's use the calculator to divide this again. Volt over ohm will be amperes, and the amperes can be changed to milliamperes by moving the decimal point to the right 3 times. So with our answer here, let's move the decimal point to the right and you will get the answer in milliamperes. And there you go, we got our I4. And lastly, we have to take the I5. So I5 will be equal to V5 over R5. So let's write the value of V5 minus 30 volts over the R5, which is 300 ohms. And we will get the answer over here by the calculator. Volt over ohm, that will be also negative. And by the way, when it's negative, it's just with regards to the direction of the current. So never mind, at least we got the correct answer for the values. And the negative will just means that it means that the direction of the current we have chosen is in the opposite. It must be in the opposite to be correct. And there you go. That's how to do nodal analysis and calculation of currents and voltages using nodal analysis. And this technique can be proven, if correct, if you do it in multisim. And in our other video, I have shown how to do the circuit for this particular circuit with a voltage source and current source, and you may check and you will see that the values of my currents and voltages I have calculated will be equal to the measured values in multisim. So I hope you subscribe in our channel and support us. Thank you so much and have a nice day, everyone.